Welcome to EE331, Lesson 34, Physics of Diodes. Diodes are the most simple semiconductor device, and the most basic function of a rectifying diode is to act as an electrical check valve. Diodes allow current to flow in one direction and block the current flow in the opposite direction. The direction of current flow is from the positive terminal, called the anode, to the negative terminal, called the cathode. Here we see a picture of a real-life diode. And this is the diode expressed on a schematic, with a triangle pointing in the direction of current flow and a blocking wall that prevents flow in the opposite direction. The voltage of a diode is always expressed with the positive on the anode side and a negative on the cathode side. A good analogy is a flapper valve for a pool. It allows the flow of water in this direction when there's positive pressure on the left. Conversely, it opposes current in the opposite direction when there's positive pressure on the right. Semiconductors are materials that have a conductivity less than most metals, but greater than good insulators. Typical range of conductivity for semiconductors is between 10 to the minus 6 ohm meters to 10 to the 4th ohm meters. Natural semiconductors such as silicon or germanium fall under group 14 of the periodic table and are commonly called group 4 atoms. Other semiconductors are formed of compounds in groups 12 through 16, such as gallium arsenide. Those are called group 3-5 semiconductors. Pure or intrinsic silicon has a crystalline structure where all covalent bonds are filled. Intrinsic silicon has some limited conductivity at normal temperatures because ambient thermal energy can raise energy levels of a limited number of electrons from the covalent band into the conduction band, where they are free to move in a similar fashion to electrons in a metal material. Simply put, semiconductors can either act as insulators or conductors. Let's take a look at the two-dimensional intrinsic silicon structure shown here. In the middle we have the group 4 atom, in this case silicon, and then this represents the covalent band with 4 electrons that are shared with surrounding atoms. Semiconductors are particularly useful when doped. Doped semiconductors are also called extrinsic semiconductors. Doping a semiconductor with an element that includes more valence electrons than the primary conductor is called N-type doping. The impurity, such as phosphorus in a silicon structure, brings an extra valence electron into the structure. Therefore, the impurity atom is known as a donor because it donates an electron. The extra valence electron has no place available to bond with the neighboring silicon atoms and is therefore free to move about. And this free mobile electron increases conductivity. The N-type designation relates to the negative charge of the excess mobile electrons generated by N-type doping. The two-dimensional construct of the N-type doped silicon shown here has an extra electron in the valence band added by the donor atom. Doping a semiconductor with an element that includes less valence electrons than the primary semiconductor is called P-type doping. The impurity additionally accepts one electron from a neighboring silicon atom and is therefore known as an acceptor atom. The vacant bond is known as a hole. The hole can be viewed as an extra mobile positive charge able to shift within the structure. This increased mobility of positive charge also increases conductivity. The P-type designation relates to the positive charge of the excess mobile holes generated by P-type doping. Let's examine the two-dimensional structure of P-type doped silicon shown here. We've added a group 3 acceptor atom, such as boron, to a silicon structure. Boron only has 3 electrons in the valence band. Therefore, it lacks an electron here. The absence of that electron is called a hole. The movement of a positive charge in this structure can be likened to the movement of a hole in a traffic jam. As each car moves forward to fill the hole, it appears that the hole is traveling to the left, when in reality it's actually the electrons or cars moving to the right to fill the hole. In both types of doping, charge mobility is increased, but net charge is still zero, since impurity nuclei have an equal number of protons and electrons. A diode is constructed of N-type semiconductor immediately adjacent to P-type semiconductor, with metal contacts on the far ends of each region. The interface between N-type and P-type regions is known as a p-n junction, which is the key area of the diode and is also the building block for more complex semiconductor devices. A diode under zero bias, that is, when the diode is not attached to an external source, forms a depletion region at the p-n junction. A depletion region is an area with no free mobile charge carriers, either electrons or holes. The depletion region is shown in the center here, with the P region on the left and the N region on the right. The diode faces to the right in this case. The depletion region forms because the excess electrons in the N region nearest the junction cross over and pair with the nearest holes and vice versa. This pairing can also be viewed as the ionization of donor atoms, now with a charge of +1 due to their loss of electrons, and acceptor atoms, now at a charge of -1 due to the gaining of an electron. The diffusion of electrons from the N region to the P region and holes from the P region to the N region give rise to ionized acceptors and ionized donors. The ionized atoms form a layer of positive charges at the edge of the N-type and a layer of negative charges at the end of the P-type that form a barrier against further movement of charge carriers in the form of an electric field. Now let's look at the middle case, which is called the reverse bias. Unlike a simple metal, a semiconductor diode has polarity and will block current flow if the polarity of applied voltage is negative with respect to the voltage of the diode. Applying a negative voltage VD is a condition known as reverse bias. Under reverse bias, the free electrons in the N region are pulled farther away from the junction. Likewise, the holes in the P region are pulled farther away from that junction. This action increases the width of the depletion region, which is devoid of charge carriers and therefore acts like an insulator. Under reverse bias, the diode blocks current flow similarly to a check valve blocking fluid flow under reverse pressure. Let's examine the two-dimensional construct of the diode in reverse bias condition. Here we have a voltage source hooked up to the diode with the positive terminal attached to the N region and the negative terminal attached to the P region. The positive terminal draws excess electrons towards the contact, and the negative terminal draws excess holes towards this contact, which results in a widened depletion region. This prevents the further diffusion of electrons or holes across this region. Finally, let's examine the diode in the forward bias condition. Applying an external positive voltage with respect to VD is known as the forward bias. Under forward bias, the electrons in the N region and the holes in the P region are pushed closer to the junction. This action reduces the width of the depletion region. If the external voltage is large enough, electrons in the N region and holes from the P region will cross the depletion region and combine. Since electrons with a negative charge travel from the cathode to the junction and holes with a positive charge travel from the anode to the junction, there is a net flow of positive charge, equivalent to a positive current, ID, flowing in the diode. Under forward bias, the diode allows current flow similarly to a check valve passing flow under forward pressure. Let's examine the two-dimensional construct of a diode in the forward bias condition. We have a positive source hooked up to the diode with the negative side touching the N region and the positive side touching the P region. The negative terminal will force electrons toward the depletion region, and the positive side will force holes toward the depletion region. This results in a narrowing of that region. Now majority carriers can diffuse across the junction from the positive to the negative side, resulting in a positive current flow. The net result of p-n junction physics is that a diode is an electric check valve with current ID that is a nonlinear function of voltage VD. In the forward bias condition, when VD is greater than 0, the applied voltage is a small positive value, but not sufficient to overcome the internal energy barrier. We'll first examine the forward bias condition when VD is greater than 0. When the applied voltage is a small positive value, but not sufficient to overcome the internal energy barrier, the depletion region incrementally narrows, but only a tiny amount of current actually flows. That's this area here. When VD is starting to grow, current is starting to flow through the depletion region from left to right. Past a certain value of positive voltage, the depletion region has narrowed sufficiently to provide a low impedance path for the current. This approximates a short circuit condition. On the plot, we see that we've gone past a certain point of positive voltage and that current has begun to flow towards infinity. The value of the positive voltage required before the diode is on is known as the forward voltage drop, or VF. It is also called the knee of the IV curve. Now let's examine the reverse bias condition when VD is less than 0. When the applied voltage to a diode is negative, the depletion region is relatively wide and only a tiny amount of current flows, known as leakage current, this area here. The condition of 0 current approximates an open circuit condition. Now let's examine the reverse breakdown condition when VD is much less than 0. Past a certain large negative voltage, the diode can no longer withstand the negative voltage and breaks down, allowing large negative currents. Breakdown can destroy some diodes, but specific types of diodes known as Zener and avalanche diodes are engineered to operate in this region and will be covered later in this course. The reverse breakdown region is located here. The voltage at which the diode breaks down is approximated here. Beyond this voltage, current flows in the opposite direction, overcoming this large depletion region and flowing the opposite way.